Have you ever stopped to think if there's one single rule that absolutely everything in the universe has to follow? I'm talking everything, from giant exploding stars all the way down to the phone in your hand. Well, there is, and it all comes down to a single, unbreakable law about energy. So let's dive in. We're going to break down the first law of thermodynamics.
Everything really kicks off with this one simple but honestly world-changing question. How do you turn fire into force? How do you take something as basic as heat and make it do something useful? Like power a machine. This question right here is basically the seed from which our entire modern world grew.
And the answer? Well, it literally powered a revolution. The whole quest to solve this puzzle is what kicked off the Industrial Revolution. It completely changed how we live, how we work, how we travel. And it meant we needed a whole new kind of science to figure it all out.
Now, what's so fascinating is that this science wasn't cooked up in some quiet, sterile university lab. Nope. It was born in the grime and the noise of the 18th century by engineers who were just trying to perfect machines like James Watt's steam engine. The machine actually came first, and the science basically had to play catch-up to explain how the heck it worked.
And that science is called thermodynamics. At its heart, it's really just the study of how energy changes from one form into another. You can think of it as the official rulebook for energy.
So before we can really get our heads around the first law, we need to know who the players are. It's like any game, right? You got to know the key pieces and how they're allowed to move. So let's quickly define our terms.
First up, we've got the system. This is our main character. It's whatever we decide we're focusing on. It could be the water boiling in a pot, the gas inside a piston, or even an entire jet engine. It's the star of our show.
And, well, if the system is our star, then the surroundings are pretty much the rest of the universe. It's everything outside the boundary of our system that can interact with it, by giving it energy or taking energy away.
Okay, I know this page looks a bit dense, but it's showing us a really important idea. On the left, you've got a closed system. Just think of a sealed can of soup. You can heat it up, transferring energy in, but no actual soup gets in or out. But on the right, that's an open system, kind of like an air compressor. There, both mass, the air, and energy are flowing in and out. This difference is absolutely crucial.
Next up is work. Now, in physics class, you probably learned it's just force times distance. But in thermodynamics, the definition is a little more elegant. Work is organized energy transfer. It's energy that's focused on doing one very specific thing, which can always be boiled down to the simple idea of lifting a weight.
And here is a perfect picture of that. Our system, the battery and the motor, is using its stored chemical energy for one single organized purpose, turning that little pulley to lift a weight. That is what we mean by thermodynamic work. It's focused, it's orderly.
So if work is organized energy, its counterpart is heat. And heat, well, heat is disorganized energy. It's the chaotic, random jiggling of molecules. And it only ever flows one way, from something hotter to something colder. It's still an energy transfer, just without that single focused goal.
All right, now that we've got the lingo down, we can get to the main event. For hundreds of years, people were chasing this dream, the ultimate free lunch machine. But it turns out a fundamental law of the universe says, sorry, no free lunch. When it comes to energy, the universe always balances its books.
This was the absolute holy grail for inventors. A machine that once you give it a push, would just run forever without any fuel. A device that could literally create energy out of thin air.
And this is what they were chasing. The textbook calls it a perpetual motion machine of the first kind, or a PMM1. The idea is simple, even if the drawing looks a little weird. The engine on the left is doing work, but look, there's no energy coming in. It would be this magical, infinite source of power. But as we all know now, it's completely impossible. And why is that?
Because of this, the first law of thermodynamics. This is the final word on the subject. You can't just make energy from nothing, and you can't make it vanish either. All you can ever do is change its form, from chemical to electrical, or from heat into work. Energy is conserved, period.
And this incredible law wasn't just a single aha moment. It was a puzzle that scientists pieced together over decades. It kind of started with Count Rumford, noticing that when you bore out cannons, the friction created a seemingly limitless amount of heat. Then this guy, James Joule, did these incredibly careful experiments showing the exact trade-off between mechanical work and heat. And finally, Hermann von Helmholtz put it all together and gave us the formal law we use today.
Okay, so this is the really important part. This isn't just some dusty old rule from a science book. It is the fundamental operating system for our entire technological world. Let's just look at a few quick examples.
Take a turbine in a power plant. You see in this diagram, you've got this high-pressure steam which is packed with internal energy flowing in. As that steam expands, its internal energy gets converted into the rotational work of the shaft, and that's what generates our electricity. Energy in has to equal work out. The books are balanced.
Or how about something like a rocket nozzle? Don't even worry about the equations on the side. The principle is exactly the same, it's just for a different goal. It takes all that hot, high-pressure gas from inside the engine and converts its internal energy into kinetic energy. In other words, pure speed. It's trading heat for velocity. And the first law is making sure the exchange rate is fair.
And hey, even your car's radiator or the AC in your house is just a clever use of the first law. An air conditioner doesn't create cold, it's just a heat exchanger that's moving heat energy from one place, like inside your living room, to another place, outside. It's not destroying the heat, it's just relocating it.
So, a great way to think about all these modern marvels is that they're basically just very sophisticated energy accountants. They take energy in one form, they process it, and they output it in another, but the books always have to balance, down to the last drop. The first law is the strict, unbreakable rulebook that they all have to follow.
But here comes the twist. The first law is incredibly powerful, but it's not the whole story. It has a huge blind spot. There is a critical question that it just cannot answer.
See, the first law tells you that if you drop a ball, its potential energy turns into kinetic energy, and the total amount is conserved. Makes sense. But here's the thing. The law would be perfectly happy if a ball sitting on the floor spontaneously sucked up heat from the ground and jumped back into your hand. The energy books would still balance. So the law tells us what's allowed in the budget, but it doesn't tell us the direction things are supposed to go.
And that leaves us with this one final really nagging question. If energy is always conserved, why does everything in the universe seem to be on a one-way street? Why does a hot cup of coffee always cool down to match the room temperature? Why does it never ever suck heat from the room and start boiling again? The first law would allow it. The energy would be conserved, but it never ever happens. Why? Well, that's a story for the second law.